Okay, so how are we to think of this integral? We're think of this integral as the approximate accumulation function under a certain condition. What condition must be true for our approximate accumulation function to be the same as our exact accumulation function? What do we have to have true? Yeah?
Very small delta x.
Yep. The delta x has to be very, very, very small. When it's very, very small, these two are the exact same function. Is that a question?
Yeah, it doesn't matter if there are no partial intervals or not.
Okay, so let's talk about that. So when delta x gets very small, what about this partial interval at the end? Yeah, so now we're thinking about, we got a really, really, really small interval, and then we have part of a really, really small interval. Is there any difference between that, basically? If you're talking if you're talking at that minute of an interval size, then it's negligible, the difference between a partial interval and a full interval. So we can really, okay, watch, here we go, ready? This is pretty cool. Wham, bam, boom. All right. So now they're the same. Now they're the same, and like we talked about, we can just take away the partial interval and just say, now when the delta x is really, really small, dx, now these are virtually the same. We don't have to take into account that partial interval. Okay, so now you're going to have some work to do here. How are they the same? So what are we talking about? We said that this is, you know how fast something is changing, a quantity is changing, and you want to know how much of that quantity you have. Okay? So you're going to go through each one of these 8 questions, and in the first 6, you're going to find each, so like for number 1, you're going to find, we know how fast something is changing. How do you see that in the integral function version? And how do you see that in the summation version of the function? We know how fast something is changing. And then number 2, we want to know how much of it we have. How does that show up in the integral definition of the function? How does that show up in the summation definition of the function? So for the first 6, you're going to talk through how each of those ideas or entities shows up in each function, and then separately answer these last 2 questions, 7 and 8. So take about 5 minutes to talk through how these two are the same in their parts, right? How they're the same. Because they're so small, right? We said really small dx, really small delta is dx, so really small delta is dy. Yeah.
Oh yeah, it's how much accumulation how much of it we have, and where it is. It's not by 7. Which is not what part of that is once in a while indicates. Between A and A being the starting value, that's the value for A of 1 and A step. Yeah. Well, actually, no, it's the accumulation of finite. So yeah, so maybe this is change of the step 1 with J1 getting 3 times the starting value plus J1 is 0.1 times the so that's going to be
Did you get through all of them?
Yeah.
J2.
Okay, we know how fast something is changing. Where does it show up in the fx function? R, the R, right? So the output of R is the rate of change. So that whole thing and this whole thing. Remember, so this just has all. What is all this? This is just kind of a complicated, a slightly more complicated input. But this whole thing is just R of an input, right? And that input is getting us to the left side of a whole interval, right? That input gets us to the left side of a whole interval. But you have to see this thing right here, not as something scary and something to avoid, but just it's R of something. It's just the output of the function R, that whole thing. Okay? We want to know how much of it we have. Where does that show up? It's the whole thing. It's the output. Okay? So, in fact, I shouldn't have pointed at the name. I should have pointed at this whole thing here. Okay, so the output of these functions is how much of it we have. That was our goal, to have a function that its output was the accumulation of the quantity. Okay, so you could have said the whole right side, or the whole left side. Right? That's how much we have. Found by summing up. Sigma for the sum. The Greek sigma is sum. German S. They both mean summing up. Many bits of change. Where do we see a bit of change in each of these? That's your bits of change. K delta x. Delta y equals K delta x. So now our K is expressed by the outputs of the rate function. And our delta x is just a super small. So this is K delta x. K delta x. But just using the rate function to get tons, like a billion of these k's and really, really small delta x's. Delta y equals K delta x. There it is, right there. From the starting value of x, what's the starting value of x? A. It's where we start accumulating from. X equals A. And where do we stop accumulating? That's this x. Okay? X is where we start accumulating at A and we accumulate up to x, which is the input of the function. So what is the input of the function? Is x where we accumulate to. Where the accumulation terminates, where the accumulation ends. That's the input of the function. So when you put in when you let x increase, you get all these outputs, and that's your accumulation function as x increases. Okay? So x is like the right side of your interval. It's where we accumulate to. What's the output of each function? The amount of accumulation. Whoops. Wow. The amount of accumulation. I can see that again. All right, so the input is where we accumulate to. That's x, and then the output is the accumulation that the amount of the quantity accumulated starting at A, ending at x. The input. Any questions on how these are the same function in all the parts? Please.
So for 6, the current value of x.
Yep.
Would that be for the a of x, a plus j minus 1 delta x?
No, this is the left side of every whole interval as j increases.
So it's r.
This is the left side of every whole interval. So you let j equals 1, then j equals 2, j equals 3.
Value of x.
Yep, so that's shown, that's seen here in this one. You see it?
Yeah,
Yeah.
the input would be.
That's the input. The input is that the x value where we're going to stop accumulating. That's the input. Okay, get out page 11. I had you print out page 11. Okay, so see how much you can finish in 10 minutes. See how much of this you can finish. Work together. We can come around and help. All fair game for the exam. All stuff fair game for the exam. Got to have these meetings. So think of this as studying. We'll come around and help. Work together. Okay, so we're gonna let's go to GC. Let's look at number 2. So this thing right here, I'll just choose this one. Is this a function or a value? It's an amount of accumulation that occurs at a changing rate. So that rate changes, we need that b in there to signify how the rate's going to change from 2 to 9. But we're going to get a value, right? It's going to be a number. So we'll do that in GC in a moment. But this is kind of different than an expression that you've seen in the past, in that you just can't plug in a b number and crank out an answer like it's an algebraic expression. So this is kind of a different, it is a value, but it's a different kind of animal than what we've seen in the past, in your past math career. What we call this is called an open form representation. In this case, of accumulation. Okay? It's an open form representation of an amount of accumulation. Okay? So what you've been dealing with mostly all the way up to this point is closed form expressions, where you have something like this, pi r squared. That's a closed form because all you need to do to get the area is just plug in the radius and it gives you the area of the circle. That's a closed form expression. Okay? Or what's another example? 1/2 h times b1 plus b2. Area of a trapezoid. That's a closed form. You plug in H, you plug in B1, you plug in B2, it cranks out your area. But this is different. We need technology to do this for us. It's reflecting a process of cutting up that interval from 2 to 9 into a zillion subintervals and doing k delta x for each single one and adding those all up. So that's reflecting a process that we can't do by just plugging in a number and doing some algebra. Does it make sense? So that's what we mean by open form representation versus a closed form, which is just rapid fire results. Plug in a value, it spits out a corresponding value. So let's just quickly in GC do this. Look at that. So we can do our Control Shift I. So we want to go from 2 to 9 of, and I'll just use B because that's what I used, B cubed minus B, but then we need B, right? And there it is. So what is that? That's the amount of accumulation starting at x equals 2 and ending at x equals 9 according to this rate function, b cubed minus, or x cubed minus radical b. So in this is open form. At this point we need technology to do that process for us to get us an answer. That's the idea of open form. I think, was that in your reading? Was there a little bit in your reading about that? About open versus closed form. Okay, cool. And so then this one down here, number 4. Why can we do this without graphing calculator? So I made a nice picture here. Starting at -6, ending at 20. 4.7 is the constant rate from -6 to 20. So if we understand what that thing calculates, it just is a very easy calculation. Yeah?
What's the d in that function? Is that the rate or something?
No, dB is a little change in x, right? It's a teeny. It's like a infinitesimal delta x.
So like 0.00001?
Well, just small enough, super small. Yeah. So that's like delta x becoming very, very small, right?
Okay.
Okay. How do we? So why is it we can do this? What does delta y equal at a constant rate of change? K delta x, and that's what our integrals are calculating, an amount of accumulation. If we have constant rate, then we can just use k delta x. What's k? 4.7. What's our delta x? Just a really big delta x, right? 26. So that's what the value of that integral is, k delta x. We can't do that with a changing rate. So that's with the changing rate, we need to go through this whole process of step approximating function, approximate accumulation function, then very small delta x gets us the integral, and then the technology can do that process for us and get us an answer quick. Questions on this worksheet, page 11. Any more questions? All right, let's do the rest of the time. Let's work on page 12. I'll put it up. Fair game for the exam. Think of this as studying.
Here's over here.
Any questions about A through E? Look at the answers. So why is there more? So B and C are almost like the same question. B and C are almost the same question. They're just two different ways to ask it. Why is there more in the tub at t equals 7 than there is at t equals 0? Why is there more? Yes, sir?
Because it's increasing longer than it's decreasing.
Okay, not only longer, but at a so overall, if you kind of maybe thought of what the average rate was, it might be around 1, right? And for 4.2 minutes. And here you might look at the average rate is like a half for less time. So it's an observational question. On the average, your rate is about 1 as it fills up for a longer time than at a lower rate of decrease for a shorter time. So you had more increase than decrease. Therefore, the least amount of water in the tub is at the beginning because you had an increase and then a little bit of decrease. Does it make sense? Okay, how about these functions? So if we want the input to actually be t, then we need 0 and t and some other different letter in here. And then this function is just going to be the same function as that one plus start with 14. It's always going to be 14 greater than this one. Okay, there's a couple more questions. Change in volume of the water. Integral notation. From what to what? 1 to 3 of? Let's just use f of t. F of t dt. Or f of x dx. Or f of a dA. Whatever you want, okay? And then we're going to use the original function, which I called v1. Is that right? And what does that equal? Final volume. V1 of 3 minus initial volume is the change in volume. Two different ways to write that change in volume. Do I add 40 or if there's a starting volume, do I add it here?
No.
No. We want just the change starting at 1, ending at 3. That's irregardless of how much was in the tub to start. So you're not going to add. Okay? To find the value of the expression, so we would put in 1 to 3, and then this 0.03 t squared minus, you can do it. Control-Shift-I, change all the parameters to make it look like that, and it should give you a value, right? That will be the total change in accumulation starting at 1, ending at 3. Will it be positive or negative?
Positive.
But it's going down.
But it's increasing.
Positive. Positive rate means the volume's going up that whole time, 1 to 3. See you tomorrow. Study.